The XPS of copper finds it difficult to discern the difference between metallic forms of copper and copper 1+ oxide. So to investigate this, what we're going to do is perform a sequence of measurements where we have taken a copper 2+ oxide which has been sputtered using an argon ion gun, and the idea is that at the center of this sputter zone we have metallic copper, and as we move along a line scan we end up with the copper 2+, and somewhere in between we have copper in a suboxide state. And we've got data now that allows us to interrogate the changes in this material using Auger lines, and we've also got valence band and a range of other measurements that we've performed, but we're going to focus on the Auger lines right now. And we've combined a pair of Auger measurements, actually at different step sizes, so that we didn't have to spend so much time acquiring the broader features of these Auger lines, and we could focus on these more characteristic shapes for the Auger line for metallic, where we have some structure there that we would like to capture. Hence we've targeted our acquisition, and we've now combined these data and performed a principal component analysis so that we can see how many abstract factors can be generated from these data. And we can see there are between 3 and 4 abstract factors that might be significant to these Auger lines. The 4 is probably related to the oxygen peak, where we've got more going on in the copper 2+ oxide than simply oxygen. I think there's nitrogen and carbon also there, so it's not surprising the oxygen peak is more involved. But using this PCA analysis we can do a noise reduction step, so we can end up with a set of corresponding data where we've reduced the influence of noise on the data by reproducing using 4 abstract factors. And the idea is that we can then perform some calculations and work out the different oxidation states for this copper. And this applies to other materials. Here's an example of molybdenum. We've got molybdenum Auger lines from a silver anode, and they could be analysed in a similar fashion to this copper. And similarly you've got gold. Gold produces a sequence of Auger lines from a silver anode that allow us to work out the difference between oxidation states that might not exhibit in the normal photoemission lines. Although these data contain different shapes, what we're going to do now is use different spectra to work out more representative shapes for the different oxidation states of copper that we believe to be in here. So we've worked out a sequence of spectra that have been calculated from the 2 that were in the active tile, and they represent a blend and the difference of those blends of those spectra, so that we can step through and look for shapes that maybe enhance the oxygen peak or remove the oxygen peak. In this example we've tried to produce a more pronounced oxygen peak, so that this is going to be more characteristic of the copper suboxide that we anticipate. And similarly we can look for another form, another shape, where we try to reduce the influence of the oxygen on the metallic form, because there should be no oxygen, and unfortunately we can't actually remove the oxygen here. We don't have a good enough overlap between the different oxide and what we have in the metallic form, so we're going to have to accept a little bit of oxygen here. But nevertheless we've been able to probably enhance in some way the metallic shapes in the Auger lines. So we're going to save these 2, and you can see already from this calculation we've got quite different shapes here for the metallic and this suboxide. So the next step we need to do, having copied those through to the original data set, is now look for the copper 2+ type shape, and we'll do this by choosing 2 that are mostly copper 2+, that's at the end of the line scan, and one that's got some 2+ in it and is near the edge of the sputter zone. So we do the same calculation, we do different spectra, and we can look through, and again you can see clearly we've got an oxygen peak that is showing much information about the oxygen, and therefore we think we've got something that is characteristic of this copper 2+. And again we have to then use an element of judgment here, but in reality the choice of this line shape has been determined by repeatedly performing these data treatment experiments and using the 2p, the 3p, the valence band, and so you build up a picture of what it ought to look like for this particular type of copper oxide. So having chosen one of these, we'll just go and have a look at what this same calculation will do for the interpretation of the suboxide. So we're going to step through and past the influence of the 2+ and see if we can remove an amount of 2+ from the suboxide that we selected, and come up with an Auger line shape that ought to be similar, very similar to the one that we calculated from the metallic and the copper 1+, or the copper 1+ like suboxide. And having done that, we can copy these through to the original data set, and we'll just do a little comparison to make sure that what we've done so far makes sense. So overlaying the data and comparing, we need to select from this set of 4, we need to select 3 line shapes that we can use as the basis functions to reproduce the original data. So having made a choice, what we're going to do is overlay the 3 basis functions in the active tile, and these 3 look like we've got very significant changes in shape for these Auger lines. So we believe we're going to produce something that will reproduce these data. These are the original raw data, and we want to overlay the basis functions in the active tile, select the raw data, and then we'll perform a linear least squares analysis, which will create a table that will decompose the data into the 3 components that we had displayed in the active tile. So each row is a linear least squares solution within this new file, and the idea is that the first column is the raw data, the second one is a linear least squares solution, and then we've got 3 basis functions in the next 3 columns. And what we're going to do is profile, using these linear least squares solutions, these spectra by creating regions for the basis functions that are aimed at a particular peak. And you can see that we've actually reproduced the data very nicely, and it's much smoother than the data itself, and that's because of the PCA calculation. If we hadn't done a PCA calculation, you'd have found that the basis functions would have been much noisier, but because we had such a large data set, we were able to remove an element of the noise, because we really had invested a significant amount of time in the acquisition process, that if you just focused on one particular spectrum, you would not take advantage of that acquisition time, but the PCA has been able to do that. So adding these regions now for the Auger peak, and this we've just chosen the primary Auger peak here, well actually peaks should we say, there are many peaks beneath these, very complex structures, you'd never want to peak fit these, but we can put regions on, estimate the intensity associated with these different Auger structures, and then we can create a profile. And in order to do the profile, we want to name the different regions so that when we create a quantification table, the traces all have the appropriate names. And we need to propagate these to all of these regions that we just created, to all the 3 columns of basis functions. So we overlay the regions, spectra with regions in the active tile, and then we'll use it propagate and match so that we pass the appropriate region to the appropriate column in the right hand side. And having done that, we can then create a profile table, and then we can create from that table the profile itself. And it is now clear that we have been able to differentiate nicely between the metallic form, the suboxide, and also the copper 2+.